All right, welcome everyone. Maybe someone can tell me, what do we know about hurricanes and global warming?
Perhaps as the Earth warms up, you get more hurricanes.
More hurricanes, what else? Yes?
Stronger.
More and stronger hurricanes. Okay. Remember this as we go through the class today. First of all, some motivation. So some before and after pictures of hurricanes. Okay, you get the idea. Here's another one, Hurricane Harvey, 2017. So now it's going to be an after and then before. Look at this picture here. This is just one of the roads. And this is what it looks like in normal times. And these are normal times. Look at this. Pretty impressive there. Okay, I wanted you to pay attention to this one. Look at the water level under the bridges, right? The water touches the bridges. This is during or so, but here's what it looks like in normal times. Pretty impressive, isn't it? Okay. And here's a typical headline from the New York Times saying humans are making hurricanes worse. And that's consistent with what we've heard so far, right? That there are more of them and they're stronger. And the New York Times seem to agree. So how about if we go through the first workshop and you tell me if this sentiment that we just heard about is correct or not. Okay, if you don't mind, let's stop calculating for a second. We'll get back to that soon. How many of you plotted the number of hurricanes as function of year? Many, okay. What did you find? You might say that it's decreasing. I think it's just not changing would be the first statement, right? Here, let's look at it. So this is it. Essentially no change yet. Interesting, isn't it? What about the magnitude of hurricanes? Let me show you that. So this is the red line here. The blue line is the sea surface temperature over the appropriate part of the Atlantic Ocean. And the red line is the magnitude of the hurricanes. We'll talk exactly what that is. It's called the power dissipation index, and we'll understand a bit later what it is. Does that show an increase, decrease?
Seems like a moderate increase for both.
Possibly because this peak in 2005 was really dramatic. But if you look, not at the smooth version, you look at the unsmooth version, you see peaks in this period and so on. So it's not obvious that there was change yet. So what we're going to see today is that we are expecting, based on very simple physics, hurricanes to get stronger in the future. But the warming so far has been 1.2 degrees approximately. That's just not enough for us to see that effect. Does that make sense? So now you plotted it yourself, you saw it yourself, you understand. Okay, so what we're trying to do today is to understand why is it that we are expecting them to get stronger. So let's talk about hurricane development. How do hurricanes develop? That would help us understand later how their magnitude depends on the temperature, okay? So it's going to be a short video, and then we'll go through everything in the video carefully on the board. Great. So now let's go through each of these steps carefully to try and understand the steps in which, the stages in which a hurricane develops. So first of all, this happens in an area of the ocean that's relatively warm. That's important, as you'll see in a second, because this leads to more evaporation, and this allows the evaporation is basically the fuel that keeps the hurricanes going. So first thing we need is warm tropical water. They start as a weather perturbation that comes off Africa. In the case of the Atlantic, and then that perturbation, once it travels over the Atlantic Ocean, can be amplified by this evaporation, as we'll see in a second. So the first thing that happens as you go over the ocean is you get this atmospheric convection. So what is atmospheric convection? Let me try to explain that. So this is up, and here's the surface, the ocean basically. And the ocean evaporates, and then you have an air parcel here that's very saturated with moisture, okay? And it's warmed from the ocean, and because it's getting warmed by the ocean, it becomes warm and light, and it starts rising. Okay, what happens? And then when it starts rising, it encounters a lower atmospheric pressure, because the higher you go in the atmosphere, the lower the pressure. Okay, so far so good. Okay. What happens when you take air and you lower the pressure? What happens to the temperature of the air?
Decreases.
It decreases, right? You lower the pressure, it cools. Okay, so if it cools, can it contain more moisture, less moisture at that point? Less. So what happens if this was very close to being saturated before, some of the moisture has to condense, right? So we get droplets here. Okay. The transition from water vapor to droplets involves the release of heat, the latent heat of condensation. So this means heat is being released. And then the parcel gets warm again. It's heated again by this release of heat due to the condensation. And then it becomes buoyant again, light and buoyant, and it rises again. And then the same thing happens. It encounters a lower pressure. It expands, it cools, condenses again, and so on and so forth. And this happens until it basically exhausts all of its moisture, and that happens at a height of a few kilometers. Okay? So that's atmospheric convection. That's at the heart of the hurricane process. Any questions about that part? Okay, so let's continue. So that was step number 3. Step number 4 is this rising of air leads to the formation of this vortex. Let's try to understand why the rising of air leads to the formation of vortex. So in this case, we want to look at the different set of coordinates. This would be east. This would be north. And we have a rising motion in the center. So I'm drawing the tip of an arrow going upward out of the board. Okay, this means that you have to have air going toward the center along the surface, replacing this air that's rising, right? So this is the center of the storm. Air must be coming toward the center to replace the air that's going up. Okay, great. Now, we're on a rotating Earth. Everyone has heard about the Coriolis force. Coriolis force acts to the right of the motion in the northern hemisphere. So this means that this motion would be directed to the right by the Coriolis force. So this would go in this direction. And now we developed a circular motion here in this direction. Okay? And the stronger the rising motion, the stronger this circular motion. Questions? Okay, so that's the next step. Number 5, so the spinning winds get stronger and stronger and so on. Let me add one important point here. The idea is this: when the wind is stronger, there's more evaporation. Evaporation depends on the wind strength. And if there's more evaporation, then the engine of the hurricane is stronger, you could say. So the rising motion is stronger, and therefore the winds will get stronger again. So there's a positive feedback, right? There's stronger winds. So stronger winds lead to more evaporation. This leads to stronger rising motion. Because remember, the rising is fed by the condensation, and you have more condensation if there's more evaporation, right? Okay, and if there's stronger rising, there's stronger winds. So there's a positive feedback. You start with stronger winds and you get even stronger feeds. So this feeds on itself, and that's why the hurricane amplifies very rapidly, and within just a few days, it could become a very, very significant hurricane. Okay, so I think that's basically the mechanism. We still need to quantify it by writing a formula that describes this process in a second. Any questions about this? Okay, great. Okay, so categories of hurricanes and the damage that can be caused by each. What we want to understand now is how do we quantify this mechanism in a way that allows us to estimate how hurricane magnitude will change when the climate warms. That's the purpose right now, okay? So we're going to write the energy balance of a hurricane. So what's the source of energy for a hurricane? What's the sink of energy for a hurricane? We make them equal to one another because basically source has to be equal to sink to first approximation. And then from that we deduce the dependence of the hurricane strength on the wind. That's the big picture. Any questions about the big picture? Okay, let's start with, so First of all, qualitatively, the source of energy is this evaporation, because the evaporated water would go up in the atmosphere, would condense, release heat. That heat is what drives the hurricane. So that is the source of heat, is the evaporation. Okay, the sink of energy is the friction at the surface. These winds blow along the surface. The ocean is rough, wavy. There's friction between the atmosphere and the ocean. That leads to dissipation of energy, and that is the sink of energy. Is the big picture clear? So we have a source, we have a sink, they must be equal to one another. The source is evaporation, the sink is friction. So let's now start formulating this in terms of equations, simple equations, so that we could write an equation for the strength of the hurricane based on that. So let's start with the sink. So the sink is due to the friction. The frictional force due to surface winds can be written like CD times the density of air times the wind velocity at the surface squared. Okay? So CD is some empirical coefficient, the density of air, and then the wind squared. This has the units of force per unit area, hopefully. Okay? Now, if you think about it, we have a force. What is the expression for the work done by the force? Say again? Force times distance. Okay, so work by force is equal to the force times distance. And think about distance means the distance air traveled across the surface, right? And if we wanted that per unit time, then I divide this by unit time. What does this become?
Velocity.
This is velocity. And therefore the energy loss per unit area time is this times another velocity, so it's going to be CD rho air times Vs cubed, and let's call this D for dissipation. Okay, that's half of the problem. Someone asked me an excellent question before. Let me go back to this. Now we can understand what this PDI that you guys calculate, what it is actually, right? I didn't say what it is. All I said is that it's a measure of the strength of the hurricane. It's actually the power dissipation index is essentially the D that we had on the board before. So it's the rate of dissipation of energy by the hurricane, which is a measure of its magnitude cubed. If you think about it, the V cubed is the rate of energy lost by the hurricane. It's also reflecting to some degree the energy put into destructive forces at the surface, frictional forces. So in some sense, this is also a measure of the destructiveness of the hurricane. So it's cube in the wind velocity. Thank you for asking that question before. I forgot that. This is the dissipation. Now we need to come up with an expression for the source of energy. This is the sink of energy. Any questions about the sink of energy?
The S, is the S just sink? Is that the velocity?
No, S here stands for surface.
Oh, okay,
So this is the wind at the surface. So this thing here is the friction force that is felt by the air per unit area. You know, everything here is the hurricane is huge. We're looking at, say, a meter square of surface of the ocean, and this is the friction between the air and the surface the friction force between the air and the surface per unit area. And it makes sense that the stronger the surface wind, the stronger the force is, right? And then to get the units right, you have to multiply it by the density, and this is something that adjusts the numbers so that it actually is equal to the force. Again, it's an empirical formula. The process involves turbulence in the air. It's complicated, so it's an empirical relation. But it makes sense that it would depend on the velocity. would we be able to guess easily that it would be velocity squared? It's not obvious, but that's what it is. That's why it's an empirical formula. Okay, so that's the force. Okay, now we know that the work done by a force is the force times the distance. So if we have work done by force is this force times the distance traveled by the air, but we're interested in the work done by the force per unit time. This is the energy lost per unit time. So I divide this by unit time, and then I have distance traveled by the air divided by unit time, and that's a velocity. So now I get another factor of velocity, and that's why the dissipation involves Vs cubed. Okay. So we know what the energy sink is. Let's deal with the energy source now. Okay, so again, qualitatively, let's remember why evaporation is the source of energy. So water is evaporated from the ocean. There's a rising motion. This air goes up in the air, and then the moisture that evaporated, the water vapor, condenses into droplets. What happens to these droplets, by the way? And rain. So some of them would eventually even drop down as rain. Okay. The condensation of water vapor, which is a gas, into water droplets, which is a liquid, involves the release of heat, right? Okay. That heat is then transferred into the atmosphere, and this is the source of energy for the motion of the hurricane. So that's why evaporation is the source of the energy. Does that make sense? Qualitatively first. Okay, so now let's try to do this more quantitatively. So we start with the saturation specific humidity. Let's call this quantity Q star of T and P. T is the temperature of air. P is the pressure of air. And Q is equal to the weight, you could say, of water vapor per weight of air. Okay, so you take a volume of air, you check what is the mass of this volume of air, and then how much of this mass, how much of the weight of this mass of air is actually the water vapor, and the ratio is the specific humidity, and this is the maximum. The saturation refers to the maximum of this expression that is possible at a given temperature. So specific humidity is this ratio of water vapor mass divided by air mass. And the saturation indicated by the star, let's explain this. Saturation means that this is the maximum amount of moisture that can be held in air in these units. Okay. And you're going to be plotting it later. This is referred to as the Clausius-Clapeyron expression, and this quantity is exponential in temperature. So it looks like this. If I plotted Q star of T versus T, it's going to look like this. There's an increase of about 6% per degree Celsius, roughly. This exponential structure is the reason we expect hurricanes to get stronger in a warmer climate, as you'll see soon. So now we understand saturation-specific humidity. The next step is to understand how evaporation depends on different factors. So let's see. We can write evaporation as follows. So this is the rate of evaporation is going to be equal to some empirical constant again, times the wind velocity at the surface, Vs like before, times Q star of T and the surface pressure minus Q. So again, the evaporation is equal to the difference between the saturation, so that's the maximum possible air, and the moisture of the air itself, okay? And then it's multiplied by the wind, because the stronger the wind, the more evaporation, and then there's this empirical constant that converts all this to an actual evaporation rate. Okay, now this is the rate of evaporation. We want to turn that into heat. So if you now condense all of this vapor, so we're evaporating at some rate. If we now condense all of this, how much heat would be released? So to turn that into heat released by condensation of the evaporated water, it's going to be the same quantity, Ck Vs Q star of T Ps minus Qa times the density of air times the latent heat of condensation evaporation. So that's what L is. Let's write it down. So this is latent heat of condensation. So the units of these things are joule per kilogram. So this is the heat that will be released by the evaporated water. Now this heat then turns into mechanical energy, the wind speed. The efficiency of doing that is not perfect. You can't take all of this heat and turn it into kinetic energy. There's some efficiency involved. That efficiency is referred to by as epsilon, and I'll derive that in a second, or at least discuss it in a second. But basically, the bottom line of that is the generation of kinetic energy per unit area time is this thing time the efficiency. So that would be equal to, we have epsilon is this efficiency that we'll discuss in a second, and then the rest of this expression and let's call this G. I just want to write this in a slightly different form. So this would be G is equal to epsilon rho air L Ck Vs Q star of TPS times 1 minus Qa divided by Q star of TPS. How do you call this? What do you call this quantity here?
Would be like a percentage, it's relative humidity?
It's relative humidity. It's what is the fraction of the maximum possible humidity that you could have in the air parcel that is actually in the air parcel, right? It's what the moisture that exists divided by the maximum moisture. And this is the relative humidity, so RH, relative humidity. So that's our final expression for G. The one thing I want to talk about a bit more is this epsilon, and I'll do this in a second. Again, epsilon is what fraction of this heat released by the condensation is actually turning into wind energy. So we'll talk about that in a second. But apart from that, any questions about this? So let's talk about that epsilon for a sec. Okay. Carnot cycle. The idea is this. Suppose you have a cylinder that contains gas, and you heat the gas. What would happen to the air? It would expand. As it expands, it would move this cylinder and will cause kinetic energy movement, right? And then suppose you cool the air. What would happen to the air? It will shrink, and then it will move again. Then you get the idea that by warming and cooling, you can create kinetic energy and motion. Here's what it looks like. Let's look at this a few times. So you see the colors changing based on the temperature. Okay, let's just say a few more words. So this actually has 4 steps, as I'll show you in a second, but the idea is when air is compressed, it's heated, right? And when it expands, it cools. So during some of the cycle, you add heat from the outside or you extract it from the outside, and sometimes you just let the temperature of the air evolve due to the compression and expansion. And Carnot figured out that when all of that happens, there's a certain efficiency of heat that is converted into mechanical energy. So the way this goes is you have to somehow inject heat into the system, and sometimes the system loses heat to the environment. So only a fraction of the heat injected is turning into mechanical energy, and the rest is lost to the environment. And the fraction is this epsilon, and that epsilon is equal to this ratio of the hot temperature to which the cycle arrives minus the cold temperature divided by the hot temperature. And for us, the hot temperature is the surface temperature. What's the surface temperature in Kelvin, roughly, in the tropics? What is it in Celsius? What's the temperature in the tropics in Celsius?
I was thinking 300 Kelvin.
300 Kelvin. Yeah, 25, 30 degrees Celsius is roughly 300 Kelvin. And the cold temperature is the temperature at which the hurricane is losing heat at the top of the atmosphere. That's going to be more like 200 Kelvin. So what is 300 minus 200 divided by 300? It's about a third, so that efficiency is about a third. So a third of the energy due to the condensation of the water vapor turns into wind energy. Okay? So now we can go back to that expression and take the final step. So finally, we set D equal to G. So reminder, D was the dissipation rate per unit area per unit time, and G was the energy source of kinetic energy per unit area per unit time, and therefore we can set them to be equal, approximately, obviously, and that leads to an expression for Vs. That's what we're trying to calculate. And that expression would hopefully look like this. So Vs squared, the surface wind squared, is equal to the sea surface temperature minus the cold temperature divided by the sea surface temperature. This is the 1/3 constant, times L, the latent heat of condensation, times Q star of T and Ps. This is the exponential dependence on the sea surface temperature, times 1 minus the relative humidity. And we assumed here that Ck was equal to Cd. Oops. Okay, an assumption. So we have an expression for the hurricane magnitude as function of the sea surface temperature. This dependence is very weak because it's basically a third whatever you do, but this thing increases exponentially with the temperature, and that's why we believe in principle that hurricanes should get stronger with the sea surface temperature, which obviously increases with global warming. So that's why we think hurricanes should get stronger. Should they also get more frequent? We don't actually know. There's no good theory for that. This whole thing was developed by Kerry Emanuel from MIT. A brilliant idea. It's quite old by now. But the frequency of hurricanes is a much more difficult subject, and there's no simple theory for that. Okay. Now, think about it. This increases by 6% per degree. What was the warming so far? We said 1.2 degrees. But there's a huge variability from year to year. We'll see in a second why there's a variability in hurricane magnitude. So 6% is not negligible, but it's just not detectable yet. If the warming is 3 degrees, as we expect it to be for a doubling of CO2, rough mid-range estimate, this would be close to 20%. So 20% might be noticeable. We'll see in a second what are the caveats for the 20% for global warming of 3 degrees. But 20% would definitely be felt at that point. So good luck to you guys. I'm not going to be around, obviously. But So let's summarize the whole idea of potential intensity. This expression there is the potential intensity. That is what is the expected maximum possible intensity of a hurricane as function of the sea surface temperature. So we did that by using the hurricane energetics. And we started out by developing what is the energy source. And the energy source was this G. So it's equal to this efficiency of production of kinetic energy from heat times the latent heat of condensation times this evaporation rate, written in this form in terms of the 1 minus relative humidity. And the efficiency is this ratio, which is basically a third. So that's the energy source per unit area per unit time of a hurricane. And then we have the sink, the dissipation. The dissipation is because of friction of the winds with the surface. And we wrote down the friction force, multiplied that by another velocity factor to give us the work done per unit time, and this gives us the sink, and then we set D equal to G, and we get this final potential intensity, which is the expression for the maximum wind of the hurricane squared as function of the sea surface temperature. And we mentioned that this is the quantity that grows exponentially, and therefore is the base for our suspicion that hurricanes are probably going to get stronger in the future. Okay? Any final question about this summary? Okay, great. Let's go back to computing, and then we'll talk about all sorts of caveats. So we now have a general understanding of why hurricanes should strengthen with warmer temperatures. It's a very simple argument. There are many, many caveats. Let's go through some of these caveats. So the main issue is wind shear. So let me first explain what is wind shear and why it actually matters. So wind shear is a change in the wind speed as you go up in the atmosphere, or a change in the wind direction as you go up in the atmosphere. Hurricanes are super sensitive to the wind shear. So when there is a wind shear, what happens is that the wind shear manages to introduce dry air into the hurricane. So where you have air that's rising and it's very saturated because it came from the ocean, if you inject dry air, what would happen to this convection we talked about? Go ahead.
It would, I think, desaturate the air, making it harder for condensation to occur, making it harder for the heat to release.
That's right, exactly. It would kill the engine of the hurricane because the air must saturate so that there's latent heat release, because that heat is what's happening, what's causing the wind speed. And if you make the air drier, it won't saturate, it won't condense, the whole thing won't work. So the wind shear introduces dry air into the hurricane and spoils the mechanism that we discussed before. Make sense? Okay. So that's why wind shear is important. Let me show you how important it is. So here's an example. This is Hurricane Florence, talking 2018. Let's look at this once, and then we'll look at it a couple of more times and stop in different places. So what I want you to pay attention to is this red dot that appears, that is Hurricane Florence. It's getting stronger, then getting weaker, then getting stronger again. Let's just look at it once. Okay. Now let's look at the explanation here at the bottom. So this tells us Florence emerged off the coast of Africa on September 1st. So you see this thing here on September 2nd. Intensified. By September 5, it became Hurricane Category 4. So let's go to September 5. So 3, 4, 5. Here you go. A nice red dot right here. It's very strong. Then it says a few days of increasing wind shear. So in that area, it turns out that there's wind shear. Make it weaker, and by September 7, it's very weak. So let's go to September 7. Okay, you see that it's weaker now. And then it's getting out of the wind shear area. And then it's able to strengthen again and become Category 4 again, and it hits the coast. Okay? So you can see that the wind shear influences the storm immediately within a day. If there is wind shear, that is, suppose the wind in the upper atmosphere, a few kilometers, and at the surface blow in different speeds, this will cause dry air to get into the hurricane. As the air is trying to rise from the surface, we'll have more dry air incorporated into this and will not allow the rising air to get to saturation. Remember, the rising air gets colder as it goes up. When it gets colder, its saturation moisture is going down until it's equal to the moisture of the air parcel itself. Here, let's write it down here. So here's the surface. The air has a moisture of QA. Once it's evaporated and all that, now it starts rising. As it's rising, Q star of T becomes smaller. When Q star becomes small enough, it's going to be equal to this. Once this happens, the air saturates. When it saturates, it would start condensing. That is when the latent heat release is happening. Okay, if QA becomes smaller because we inject dry air and mix it with this moist air, now the air that's rising has a smaller QA. You have to make this much, much smaller for the saturation to happen. So that was wind shear, and we demonstrated nicely for this Florence storm. Any more questions about wind shear? There's one more thing I want to say about wind shear, or a couple actually. Okay, so wind shear again. It turns out that when El Nino happens over the Pacific Ocean, this changes the wind shear over the Atlantic. So you see this telling us that during an El Nino year, the wind shear is stronger. And if you look at the number of storms, let's look at intense hurricanes, okay? So over the Atlantic, an average year would see 2.5 intense hurricanes, but if it's an El Nino year, there's only 1.5 intense hurricanes. If you just look at hurricanes, it goes down from 5.8 to 4.0. So the existence of El Nino changes the wind stress over the Atlantic. El Nino is in the Pacific, and it changes the wind shear over the Atlantic and therefore affects the number of hurricanes. So that's why when you hear a prediction of the next hurricane season, they tell you this is an El Nino year, there would be less, it's a La Nina year, there might be more, and so on. Why is it that El Nino changes the wind shear is the next question, okay? So here's an attempt to do that. This is referred to as the Hadley circulation. So this is the Earth, and this is the equator right here. And you know, the equator is warm, so air goes up above the equator and then goes down over about 30 degrees north and south. So the air goes down over 30 degrees north and south and causing the desert belts and all that. We don't need to get into that. But at the same time, this circulation affects the atmospheric jet. So sometimes you see this in weather maps. You see an atmospheric jet. There's actually a couple of them. So this is the subtropical jet. And if this is an El Nino year, the jet would look one way, and if it's El Nino year, the jet would look in a different way. And that jet that comes from the Pacific reaches this formation area of hurricanes in the Atlantic and affects the wind shear. So El Nino affects the Hadley circulation. The Hadley circulation affects the jet affects the wind shear, and the wind shear affects hurricanes. That's the logic here. When there is an El Nino, it will increase the wind shear, and that will decrease hurricanes.
Wasn't there this distinction between Atlantic and Pacific?
Yeah, that table was also showing East Pacific hurricanes in addition to, where was it? So, you know, there's East Pacific hurricanes also, and they're affected by the El Nino events differently than the Atlantic hurricanes. I was focusing on the Atlantic hurricanes, but El Nino also affects East Pacific hurricanes. What do we call hurricanes when they happen in the West Pacific? Cyclones would be in the Indian Ocean, and typhoons in the West. They're all the same thing, right? Cyclones in the Indian Ocean, typhoons and hurricanes are all the same things. Okay, we want to ask the question, will hurricanes get stronger in a global warming scenario? This time, the approach would be a statistical approach. So let me try and explain the case here. So what do we see here? We see the thick line showing hurricane strength. This would be this PDI, so basically the D that we had before. And the thin line is the Atlantic sea surface temperature. And you can see that they go together very well, actually, right? So you say, well, if they go together, there's some correlation between the sea surface temperature and the Atlantic amplitude. So I can take that, predict the sea surface temperature from a climate model, and use that to predict what the hurricane magnitude would be in the future. Why do I need to do that? Why can't I just take a climate model and predict what the hurricanes will do? It turns out that climate models that are used to predict global climate change are not fine enough. The resolution is not fine enough to simulate hurricanes correctly. So we can't use them directly to simulate hurricanes in the future. It's going to be too expensive to do that. You need a very dense grid with a very fine resolution, mostly to resolve the eye of the hurricane, and that can't be done. So instead, we use the climate model to predict the SST. Then we use this correlation between the SST and hurricane magnitude in the observed record to deduce what the hurricane magnitude would be in the future. Is the idea clear? Let's see what they get when they do that. This line here, all of these lines, are predicted hurricane magnitude based on the sea surface temperature predicted in many climate models. You take this correlation that's deduced here, you apply it to the prediction of what the model SST says about hurricane strength, and you deduce what the PDI is, that is, what is the power of the hurricane in the future for that SST. The thick line is the average over these many model estimates. So this tells you that it would increase by a huge factor. Okay? So it turns out, though, and this is the paper that's cited here, that instead of looking at the sea surface temperature in the Atlantic, it turns out that the correlation is even better if you basically correlate the hurricane thickness, which is again the thick line, instead of with the Atlantic sea surface temperature, it's now correlated with the Atlantic sea surface temperature minus the tropical. Think about it for simplicity is the Atlantic minus the Pacific or something, okay? The reason for that physically is that we know that the temperature difference between the Atlantic and the Pacific, just like in the case of El Nino, affects the wind shear. And it turns out that indeed the correlation gets better if you, instead of correlating the hurricane magnitude with the Atlantic sea surface temperature, you correlate it with the Atlantic minus Pacific SST, or Atlantic minus tropical is more precise. Okay? And look at the numbers. This has an R squared of 0.3, and this has an R squared of 0.5. So it's significantly better when you do that. Does it make sense that we correlate now the hurricane magnitude in the Atlantic with the temperature difference between the Pacific and the Atlantic, because we know that when there's an El Nino, this changes the wind shear, and this changes the hurricane magnitude, and in this it gives a better correlation, okay? Can someone please tell me, if I draw now the same picture here, what would hurricane magnitude in the future be predicted if the predictor is not the Atlantic sea surface temperature, which we know for sure will increase, but instead it's this quantity that's used here? What would the hurricane magnitude do in the future?
Would it be flatter just because if Atlantic is increasing, presumably the tropics?
Exactly, yeah. So let's look at that. So in this case, the prediction is that there's basically no increase in hurricane magnitude. Again, the reason is, yes, the Atlantic is warming, but also the Pacific is warming. So the difference between them is not changing very much. Now, this is all statistics. There's only so much you can learn from statistics. We understand the physical principles, the G and the D. We do expect these to lead to hurricanes getting stronger, but this is an interesting study that I thought we should mention.
I'm just confused as to why, they chose to look at that difference. Like, why? Yeah. Yes. Like, why is that? Is it because it's a stronger correlation that it might prove to be a better model? I just wonder.
Yeah, excellent question. I mean, they know that during an El Nino, you have less hurricanes because it affects the wind shear. So they said, well, during an El Nino, the sea surface temperature difference between the Pacific and the Atlantic changes. Let's try that. And then it turns out that it worked out nicely for them. I think this is an interesting result, so it's worth knowing about. But if you ask me what do I think hurricanes will do, I wouldn't rely on statistics that is completely blind to the physics. I would rely on the fact that this predicts an increase in hurricanes and that I know that the wind shear is going to complicate things. So I'm saying the default assumption is that the hurricanes will get stronger, but there's an uncertainty because we don't know what the wind shear will do. Okay, yeah. So you know about the IPCC report, the Intergovernmental Panel on Climate Change. These are plots from the IPCC of 2013, and what do we see? We see landfalling tropical cyclones in eastern Australia. Is there a trend here? Isn't trend here not obvious that between 1900 and 2000, over this 100 years, there isn't an obvious trend. You look at landfalling hurricanes in the United States, it's not clear there's a trend. China, it's not clear that there's a trend. They showed the record. So, and this is for a report that's super careful. This IPCC report is prepared by many scientists there, and I think they're very careful. Typically, they overemphasizing the uncertainty. So I think we can count on what they're telling us. And this is from the more recent IPCC report. So this is just text, but if you look at this, they would tell you there's low confidence in most reported long-term trends in tropical cyclone frequency and intensity due to the change at the time collected data. So, they tell you that there's an uncertainty in the data if you go far enough in time, because if you think about it, 1920, how did we know if there's a hurricane in the middle of the Atlantic Ocean where it's far from any country and so on? So it gets complicated at that point. And then this says, best track data of hurricanes that have impacted the US is reliable, but it doesn't show a trend in the frequency of landfalls over the USA. So over the USA, we do know what the numbers are, but there's no trend. Okay. This is a recent paper, Cosin et al. 2020. This is the one clear evidence that we have statistically that hurricanes are getting stronger, or at least the strongest evidence that we have. So what's shown here? They're asking what fractions of hurricanes are major. So major is categories 3 to 5. So they're looking every 6 hours at the winds. They're saying, here's a hurricane or here's a major hurricane. So, and then they're asking what fraction of these intervals of time show a major hurricane as opposed to just hurricane. Okay, so what fraction of hurricanes are major hurricanes? They're basically asking not what is the frequency of hurricanes, but what is the fraction of hurricanes that are very strong. And then you see the data here and the line fitted here. And then they actually showed in the paper a figure like that, which is this data combined into 3-year averages, and you can see a nice trend here. So the fraction goes from 30% to close to 40%. So a 10% increase in the fraction of hurricanes. The only difficulty is if you look at this, before this averaging, the averaging is sort of a trick, right? But if you look at the raw data, the R squared is 0.18. What is R squared? What is it telling us? What's this quantity telling us? Yes?
Like how much variation the line, like the fitted line, explains?
That's a very good way of doing this. Formally, it's referred to as how much the variance is explained, but basically it says to what degree that this line represent the variability around the trend. And 0.18 means that 18% of the variance is explained. So, and you can see that there's large noise around this line. It's not obvious to me that this trend represents global warming, but it does tell you that hurricane amplitude changes a lot from season to season, which we know. 2005 was huge, and the Katrina hurricane and so on. But, it is what it is. This does show a trend. People keep mentioning this as a strong evidence, and maybe it is. Yes?
What's like the general argument against increasing hurricane intensity when you look at these graphs?
No, there's a physical argument for increasing hurricane intensity that we went through.
But say if there's like a person who denies that hurricanes are like...
I see.
Yeah.
So looking at this, what can I say against this evidence? It's exactly what I said, that the variance explained is only 18%. That's the strongest argument against this. But on the other hand, it does show a 10% increase in the fraction of major hurricanes. It's consistent with the physics that we went through, this potential intensity argument and so on. So, it's an evidence that shouldn't be neglected or ignored. Okay, so we asked at the beginning, what do we know about hurricanes? Can someone tell me now, what do we know about hurricanes in a global, so today? Yes.
They're fueled by evaporation.
Fueled by evaporation, okay. Yeah.
Can be affected by high wind shear.
Wind shear is important. Yeah.
El Nino effect can actually be good for the intensity, to reduce the intensity of the hurricane.
Right. El Nino is important because it affects the wind shear. And in terms of the evidence for do we have more hurricanes, less hurricanes now? Did they already get stronger, more frequent? What do we think?
I think we talked about how there's no evidence that they're getting more frequent, but we do see that they might be, like the fraction of major hurricanes is
Perfect. Okay, so there's no strong evidence that there are more frequent hurricanes. There's not strong evidence that the intensity measured by this PDI is stronger, but this suggests that maybe the fraction of major hurricanes did increase over the last 40 years. Okay. I would say if you had to summarize it in one word, I would say it's complicated, don't you think? That's going to be the answer in most classes here. There's going to be a few cases in which we say, look, it's obvious. How could you be skeptic about that? But it's good. My purpose is to make sure you understand the uncertainty. So now you understand the mechanism of how hurricanes are expected to strengthen. You understand the caveats, which is we don't know what the wind shear will do. And you understand that it's complicated. And I hope you get the picture. So let's go through the conclusion slide. I think we said all of that. The maximum possible hurricane amplitude, which we call potential intensity, can be estimated from the energy balance, the source equal to the sink, and it's expected to increase exponentially with the sea surface temperature. Sea surface temperature increased only by 1 degree, point something so far. In the ocean, maybe just 1 degree, and therefore we didn't see much of an effect. The change in the amplitude actually depends on the wind shear and also affected by ENSO. ENSO is El Nino. ENSO is basically El Nino southern oscillation. Think of ENSO as being El Nino. The increase in the fraction of major hurricanes so far has been detected. That's what we talked about most recently. But the signal is not large, and the year-to-year variations are very large. That's the R squared being only 0.18, but this is an important evidence. And the frequency of hurricanes so far probably hasn't changed as far as we can tell. And we also don't have a good theory for explaining it in the future. Excellent. Thanks. See you next time.